This is Unit 2 AP Workbook Problem M called Limiting Cases. So there's a boy, Blake, and his little sister's in a sled here. The sled and sister all together have mass little m. There's a coefficient of friction on the surfaces, mu sub k, and there's this angle here, theta, and there's a tension they're calling capital T. There's, so now we've got this dot at the right represents the sister and sled system. Draw a free body diagram showing and labeling the forces, not the components exerted on the system. Draw the relative lengths of all. So we've got our normal force upward from the ground. We'll call that Fn. It's balanced by the force of gravity of this mass. You've got this opposing force, friction force, pointing the opposite direction. So that's going this way, okay? And we're going to make that FFK, and then this way you're going to have a tension force, okay? Now it says suppose that Blake, and this is the angle, by the way, increases the angle slightly but keeps the angle less than 90 degrees, and then they're going to debate how it changes the magnitude of acceleration. So she argues that increasing the angle will decrease the acceleration of the sled. Why this is explain why this is possible in terms of the free body diagram. So when you increase the angle, what that does is it increases the vertical component of tension, right? Because you're going to have more of that force upwards than to the right. And what that looks like is there's Ft, and then you've got this vertical component, and you've got this horizontal component. And so as you go more and more, if you made this a bigger vertical angle, a bigger angle like this, then it's going to increase your vertical component, and it makes your x component smaller. So that's correct, right? Then friction force is directly proportional to that normal force, to the normal force, right? And as you lift, right, as you have a bigger vertical component of tension, and the vertical components have to equal the vertical upward components have to equal the vertical downward components, the weight of the object doesn't change, but now tension is like causing a reduction in your normal force. So therefore, the let's say when the normal force goes down, friction force is going to decrease. So friction force, less friction means less, means more acceleration. Oops, I think I just made the case for Carlos, right? So this does not prove Angela's. Okay, so this is actually Carlos says increasing the angle increases acceleration. That's what I just proved, right? Okay, so that wasn't right. So how can we do the other way? So now let's take a look at the other component. Increasing theta causes a decrease in the x component of tension, right? Like we talked about before. So even though the y component is increasing, the x component is decreasing. The decrease in the ftx means that the x component of Newton's second law decreases, right? Because it's going to be ftx minus ff. So if this gets smaller, then this total is going to get smaller as well, which reduces acceleration. Okay, so I mixed them up, and I considered re-recording this, but you should see that I make mistakes, right? And there's nothing wrong with making mistakes, and I always want to try to be as authentic as I can so that you can see what happens. And I'm just following my train of thought. So sometimes you'll start it wrong, and then you'll go, oh, I got the wrong result. Now I better and I just proved the wrong thing. So this is, I mix these two proofs up in my mind, and that's perfectly okay. You make corrections as you go. Part C, derive expressions for the following term in terms of these variables. And so if you need more space, you can do that. So let's solve for the force the ground exerts on the system. This is Fn. We're going to solve for the force of friction, and then we're going to solve for acceleration. So we're going to write out Newton's second law on the y-axis is Fn plus Fty minus Fg little m equals ma. Y. To do this, I'm going to use the x component, like I started to kind of talk about up here. This is going to be ftx minus ffk. Notice I'm making the left the positive direction, and that's okay. You can decide yourself. So this acceleration is 0, so Fn equals Fgm minus Fty, which is mass times gravity minus tension sine of theta, using the variables that are given. We're allowed to use F pull. They changed from capital T to F sub P, so I'm just going to be consistent with what they told me at the beginning. So this is using all the things we're allowed to. So I'm going to double check that and make sure I have an expression with only the variables that they say I have to do. If you leave it like this, it's not that the physics is wrong, you just didn't answer the question. This one's going to be, tension cosine theta minus mu times Fn. This is the equation for friction equals mass times acceleration. The force of friction by itself is Fk is mu times normal, which is what I was putting in here. So mu is allowed, right? That's given. And then the normal force we just solved for. It's mg minus t sine theta. So this is part 2. This is the answer for part 2. This here is going to be solving for acceleration. So I'm going to take this expression and continue here, t cosine theta minus, I'm going to put in my friction here, mu mg minus t sine theta equals ma. Now I'm going to divide both sides by m, and I get t cosine theta minus mu mg minus t sine theta equals a, and the whole thing is over m. Now I want you to notice something. This is an ugly expression, right? There's nothing graceful about it. Doesn't simplify. That's okay. Don't worry when you get expressions that are messy, because that is not unusual.